force you'll have to represent like what is that force? Why did I write GZ? Gradient of ZZ. How did I write? Maybe 14th. If I open the 14th lecture 14, I mean on 4th. Yeah. So you have this one on 14th and then 13th. So this is what you have, right? So where is that W? Row B. B is the thing, right? So yeah, we actually, if you actually see lecture 13, we actually put it as GZ, right? Minus GZ. That's the force, right? Gradient of minus GZ. So that is the G. G is the force, right? Gravitational force. External force is by the gravitation, gradient of minus GZ, right? So, but last lecture, I think we and there itself, I think I continued to use plus G or minus G. Yeah, that is plus G. I think that's fine, no?
Yes, sir.
Minus GZ, when you bring it to this side, I think it will be plus. Yeah, I think plus GZ is correct only, right? I think it's fine. G. Minus U square. Okay. P plus G. Yeah, I think that's fine. That's fine. We have not done any mistake. I thought I missed that minus sign. Okay. So that's fine, right? Sorry to confuse. I think I mistaken. That was the right hand side. I should put. I already put minus. So this is okay. Okay. So this is what we have done. So we have taken this and the momentum equation, and for barotropic fluids, and we have given that momentum equation. So we wrote it like this is your Bernoulli's function. So we introduced the Bernoulli function. So momentum equation for barotropic fluid is like this, right? So where we introduce the Bernoulli function, and then in the process, so if you look at this one, so along the streamlines and vortex lines, this your verticity, right? So this is U is tangent to the streamlines, omega bar basically that is tangent to vertex lines. So these vertex lines and tangent lines need not be perpendicular. That's what we have shown in 3 dimensions. But in 2 dimensions, it should be perpendicular, right? So have you understood any question here? 2 dimension, 3 dimensions, whatever we have written in the last class. Any question here?
No, sir.
Okay, so then we'll move on. So we'll try to do something. What is that we'll do? Yeah, this is what you have. So this is now if you consider let's look at this. So what exactly we do now? So now consider the steady flow. Okay, so if you consider the steady flow, just give me 1 second now. So I'll
Yes, sir. But tomorrow?
notes. Okay, so what we do in this class is just to continue. So where is this one? The problems that I gave as an assignment, is it okay? Are you able to do something?
Yes, sir. Yes, sir.
Okay, so now what you do is you take that dou u by dou t. Okay, so we will consider the steady flow, whatever that equation that you have, the dou u by dou t plus gradient of this Bernoulli function, which is given as u cross omega bar, isn't it? So what I do is I try to consider only steady flow. For steady flow, so what you get is gradient of B. So that will be 0, no? So there is no time dependence for steady flow. So grad B is equal to u bar cross omega bar. Now this implies I can just make a dot product with anything, right? So I can just make a dot product with either u bar or omega bar. So if you do that, so this grad B dot product with, let us say, S cap. Okay, so this S cap dot u bar cross omega bar. So where omega bar S cap is unit vector along the streamline, right, or parallel to u. Okay, the velocity vector. So why should you take only this one? So you can also take omega side also, right? Omega direction, but that is not easy to see for the flows. Okay, so you generally take for u. Then what you are getting here is this becomes 0, right? So there's a divergence of curl is always 0. So this implies del B dot S cap, or you simply this is parallel, right? So you can write like this is equal to u bar. So u cap. Okay, so u cap equal to 0. Since this dot product, right? So the dot product of what do you call this one? Dot product of curl, right? Is this always 0? It's always true, no?
Yes, sir.
U bar dot u bar cross. So this cross product is always perpendicular to both u and omega. So which you are now making a dot product. So that is going to be 0. Since u bar dot u bar cross omega is 0. So now what is this meaning? What is this meaning? This is basically, gradient of inside certain direction is nothing but dou s, right? That's your directional derivative of B with dou s equal to 0, where s is, what is s? Or s cap. So this is basically, this is the unit vector, along this. This we have already written. So what is the meaning of this? This is the directional derivative along the streamline, okay, or along those tangents to the streamlines is 0. Okay. So what is this meaning? So what is the meaning? So B. That means B has to be constant. That means B has to be constant along the streamlines. Right? So along certain direction, if the directional derivative is 0, means what? So along those directions, whatever direction, S direction. What is S direction? Basically streamline directions. Along those if you do it along those streamlines, okay, or simply think of like this: dou b by dou x dx, okay, right? So how do you see this one? So along this one dx, so you can always write like so how do you see this one? Dx by ds, for example. Okay, so this you can write like this: dou b by dou y into dy by ds plus dou b by dou z into dou z by dou s equal to 0. That is what it is meaning, right? See this dot product with dx dy dz, dx by ds, dy by ds, dz by ds is basically a tangent to the streamline, right? So that's what it means, isn't it? Gradient dot u bar. U bar is basically dx by ds, dy by ds, dz by ds, where s is the parameter of the curve. The curve is the streamline curve. Okay. So b is basically constant. So that means what is your b now? So what is your b? Half u square plus integral dp by rho plus gz equal to constant along the streamline. So this constant may be different for every for different streamlines. This may be different constant. Okay, this constant may be different for different streamlines. Okay, so basically streamlines you have parameterized, like each streamlines, one streamline you take it streamline, you parameterize like x of s, y of s, z of s. Okay, so s is the parameter, s belongs to R. So you do it like that. So once you parameterize, dx by ds, dy by ds, dz by ds will give you actually your tangent to that curve, tangent to the streamline. So dot product is along that direction, dot product is 0. So that gives you that b is actually constant along that streamline, along that curve. Okay. So this is what you will get if you consider uh, steady flow. Okay. What else we can do? So let me see. So what is that you got here basically? So from here, so you got your Bernoulli, right? So if you consider irrotational flow, incompressible flow and irrotational flow, if you do, you got your Bernoulli function basically. That b will give you along with a time derivative also, right? So you need not be steady flow. So yesterday you have seen that, last class you have seen that you already got the Bernoulli equation. That's called Bernoulli equation. So this here, because we are not able to do anything in this case, so what we are saying is this is only b is called Bernoulli function. So that's why to do something we consider only steady flow. Steady flow will give you this constant will be different. Okay. For irrotational flow, this constant is same. Okay. So just make a point for irrotational flow. This constant, whatever constant you have now. So that's, I think we have written for irrotational flow, the Bernoulli equation is constant, right? So Bernoulli equation, whatever you got earlier, Bernoulli equation, that is actually constant everywhere. Okay. So Bernoulli equation for irrotational steady flow. So for example, just to make a point here, so for irrotational steady flow, so what you get is half u bar square. Square means that modulus. Okay. So Okay, so this will be equal to this one plus integral dp by p plus gz equal to constant everywhere. Okay,
सर डीपी बाई रो या डीपी बाई पी?
dp by rho, dp by rho.
ओके सर।
That is dp by rho. Why is this constant everywhere? If there is no vorticity, that means there is no irrotationality, right? So suppose that is if w is 0. I mean, right? That's what omega we use the omega. So omega is equal to 0. Omega, which is del cross u, equal to 0. So in this case, you see that this thing will be constant everywhere. What could be the reason?
Because sir, our equation del u by del t already zero and grade b equal to u cross omega. Omega equal to zero, then grade b equal to zero, then b equal to constant, sir.
That's there everywhere. So not on all directions it is same. The moment you put omega is 0, you don't have to multiply with anything, no? So all direction s can be anything. Okay,
Yes,
s need
sir.
not be in the only along the streamline. So it's there every in all directions and all along all curves. Basically, it is 0. Okay, this is true del dot b. So if you look at this del b, I mean gradient b dot s cap equal to 0 for all of omega equal to 0. That's all directions it is same. That means basically gradient, that derivative itself is 0, right? So that means grad b itself is 0. That means b is constant. So that is what you are writing here. Okay. So you make that point. So something called stream function we'll define now. Okay. So in the case of three-dimensional flow. Okay. So let's consider if so far did we use del dot u equal to 0? We have not, right? Well, how did we derive this Bernoulli equation? Basically through this momentum equation only, no? Momentum equation only. So along with that, if we have del cross, I mean the del dot u is also 0. That is for incompressible. If this is true, then we know by Helmholtz theorem. That's what is I have given as a assignment. Then there exists a vector field. What is that vector field we denoted? Let's call this V, right? We did V, right? V such that U equal to this. This is the cross product. Okay, this is what do you call this? This one curl of V. Let's call this. This is this one. Okay, so this will be in 3 dimensions. Okay, so in 3 dimensions. So what will happen in 3 dimensions? This is not unique, right? In 3 dimensions. So 3-dimensional flow, if you consider incompressible flow, then there exists a vector field V such that U is del cross V. This V bar is not unique by Helmholtz theorem. That's what we have written, right? So Helmholtz theorem tells you that, that theorem that is for the last 2 roll numbers that I've given as an assignment, that any vector field you can write it as this curl. This is your basically this is your rotational part, and there is an irrotational part. So if you add that one, so you can always do this one. So, okay. So if you add any del cross, okay. if so, okay. So here, what is your Helmholtz theorem tells you? What is your Helmholtz theorem? That I already sent you, no, by this thing. Forget about the Helmholtz theorem. Helmholtz theorem gives you that it is not unique. Okay. Helmholtz theorem itself tells you that it exists. Okay. So by Helmholtz theorem, this exists. Okay. So you don't say it is not unique. So V exists by Helmholtz theorem. By Helmholtz theorem. So if we add any gradient of scalar function, okay, phi, where phi is scalar, to V, then still del cross. So what do we do? So this one plus grad phi. What is this one? This is actually del cross V only, right? Which is still U only. Because since del cross del phi, is it 0? Hello? Curl of gradient is 0, right? So these are the standard results, okay? Since this is always true for every phi. Okay. So you don't gain anything here. So there is no unique V. Okay. So there is no unique V. That implies there is no unique V. What happens? Situation will be different if you consider 2 dimension. Okay. So but for 2 dimensions, so what happens in 2 dimensions? As you have already seen now, last class, for 2-dimensional flow, del cross something, right? That is basically vorticity. Vorticity will be, if it is in the confined to, in 2-dimension means flow is only in the 2 dimensions. So your del cross A direction is always in your in the perpendicular direction, right? Hello.
Yes, sir. Omega
So
is perpendicular to you, sir.
yeah. So where should you be? So how do I define my now A your V? V, how do I define this? V is unique. Mm, this V should be perpendicular to the flow, right? Flow in the XY plane, to the plane, flow plane. For example, you can write it as flow plane. That means V bar equal to some function only in the Z direction. So let us say in XY. That is, if you put it like IE XY plane, flow in the XY plane, then you will have then you can write it like this V bar. That is that vector field, that I can write it like some psi of xy comma t into z direction. That is your k. If you want, you can put it like k. Okay. So what is this one? So that implies u bar equal to del cross v, del cross this v, right? So this del cross v, that is your basically if you actually do your del cross V with this 0, 0, okay? So I, j, k, dou dou x, dou dou y, dou dou z. What do you have here? 0, 0, psi. This if you do that kth component, right? Ith component, what is that you get? So you can write it. Ith component will be dou psi by dou y, and jth component will be dou psi by dou x with negative sign, and kth component will be 0. So as you see, del cross V is always perpendicular to the plane direction. So this is u will be in the xy plane. So only x component, y component is there. Okay. So del cross V is basically that's how you get your okay. So if there is a plane, if in 2 dimensions, what happens? U bar will be del cross V. V is always in the 2 dimensions. Del cross V is always perpendicular. So that's why. How do I see this one? It's fine, right?
Yes, sir.
Is it okay? Yeah. So then that means what you get is basically u equal to dou psi by dou y, v equal to minus dou psi by dou x. W is anyway 0. It's a 2-dimensional flow. Okay. So this will give me. You can solve for. Now solve for. So given flow, solve for psi as a function of x, y, t. Solve for x, y in a given flow. In a given flow, that is u comma v. Okay, so only 2-dimensional flow you're considering now. So you can solve it and get your stream. So such a function is called stream function. So such a function psi of x, y, t is called stream function. Stream lines you have seen, but what is the stream function? So you say that this is your stream function because what happens here? So why we call this such a function stream function? Because it is actually along the stream lines. This is actually constant. Okay, so that you can easily see if you calculate dou psi by dou x, dou s. S is the parameterized. S is the parameterized. Dx by ds, dy by ds. That's what is the tangent to the streamlines. Then what is this one? This is actually dou psi by dou x. Psi is only function of x, y, right? So if you consider this one, so dou x by dou s into dx, that you divide with ds dou x by dou s plus dou psi by dou y into dou y by dou s. So this, if you actually see this one, dou x by dou s and dou y by dou s. What is this one? This is actually tangent to the flow, right? So to streamlines, that's tangent to, so that's tangent to the vector flow. So that will give you dou psi by dou x into, so dou x by dou s is nothing but your u. So u plus dou psi by dou y. Dou y by dou s is your v. So this will be, but you already have dou psi by dou x is minus v into x plus dou psi by dou y is your u into v, which is equal to 0. That's equal to v into u, right? So that is v into u. So uv, that is equal to 0. So by construction, as you see, the way you have taken, right? So this becomes such a function is stream. So you can now write it as so along the streamlines, this thing is 0. So that means psi equal to constant psi of x by t equal to constant along the streamlines. So if you have such a function, you say that that's called stream function. So we can define formally as a definition. You can give any function psi of x, y, t that is constant along the streamlines is called a stream function. Okay. So we'll try to give some examples of two-dimensional flows. Okay. So let's consider simple flows. Okay. Let me give some flows. Flow means you have to give your velocity vector. So let u bar equal to. So let's consider some ay by x square plus y square. So I'm considering only a steady flow here. There is no time. So x square plus ax by x square plus y square. So a is some constant. Okay. So let's call this. So a is constant. So given this, so first of all you can see that this del dot u equal to 0 or not. What is del dot u? Dou x, if you calculate and see what is dou u by dou x? This is your u, right? This is your u. This is actually your uv. So dou u by dou x plus dou v by dou y. So what is that you gain? Dou u by dou x is what? You just do that integration. So differentiation x square plus y square whole square. X square plus y square. So dou x, no, that is 0. You'll have
2
minus, right?
2xay
2,
divided by
2x
ay.
uh, 2x ay divided by this. Okay.
Yes.
Now this other one you will have plus sign, right? So other will be plus 2a yx, right? 2yax basically, right? So you write 2yax plus sign because negative is there now, so it's something similar you will get
0, sir.
y square equal to 0. So this is basically given flow is first you have to make sure. So you have done for the incompressible flow only you're working. Okay. So incompressible flow, two-dimensional incompressible flow, you can find a stream function. Okay. So the stream function must satisfy. What is the stream function now? We want to find the stream function dou psi by dou y equal to u, right? That is same as ay by x square plus y square dou psi by dou x equal to minus v, right? Yeah, dou psi by dou x equal to minus v. So minus v is and it becomes plus ax divided by x square plus y square. Now can you solve this? If you just solve this one, psi of xy, it doesn't depend now. So obviously you will have it doesn't depend on time because the given flow is steady flow is given. So psi of xy, if you do integration with respect to y, what is that you get? A times ln of x square plus y square. 1 by x square plus y square. 2y, right? 2y you will get. So you will have to put the 2 should go. So a by 2 plus some constant. That constant will be some function of x, right? Function of x. Let's call this function of x. Now you apply this one. Dou psi by dou x equal to which is equal to, you can calculate it. So this implies dou psi by dou x equal to So a by 2 into 1 by x square plus y square into 2x. 2 goes plus f dash of x. Okay, so this dou psi by dou x is already given as this one. So ax by x square, that gets cancelled. So here you can write it like ax by x square plus y square, because we know dou psi by dou x equal to ax by x square plus y square plus f dash of x. So this will give me f dash of x equal to 0. That means f of x equal to constant, isn't it? So f of x equal to constant. So constant, so that's what you got. So you have a stream function that turns out to be a by 2 times ln of x square plus y square plus some constant. Constant doesn't affect because psi equal to constant, right? So constant you can put it. So what are those stream functions? Stream function did not. So constant will not contribute, right? Finally, psi equal to constants are those streamlines, isn't it? Psi is this function. Once if you take this function equal to constant, if you put it constant again is another constant, right? So you need not worry. So constant will not contribute. So what you are getting is, so the stream function psi of xy equal to a by 2 ln of x square plus y square equal to constant. Let us say c is constant or streamlines. What are the streamlines? So that means 2c by a, that is also constant. Ln of x square plus y square equal to constant. So that means x square plus y square equal to constant, right? These are streamlines. X square plus y square. Exponential, if you take everything constant, exponential of constant is also constant, right? So these are simply constant or streamlines. So what are those? Can you draw? Those are all circles. Yeah. Now these are all circles. The direction you don't know, right? Depending on A. So A direction, the flow. So if A is positive, yeah, what is that, positive or negative? So which direction are you going to put it? If A is positive, that depends on the direction, right?
Yes, but sir, if we take exponential, then it will always positive.
See, A is positive. What did you say?
Uh, Sir, when we calculate streamlines, then taking ln x square plus y square equal to some constant 2c by a, then again take exponential, then exponential always become positive.
Yeah, that's okay. So x square plus y square equal to constant. It's always positive anyway. Yeah. This is like c square. I'll write it as some a square. Okay. Some c1 square. This is like r square type. Okay. Some r square. Positive. It's anyway positive anyway. Okay. These are streamlines. Circles. Okay. So the direction of the flow. How do you calculate? How do you make sure that this is the direction? Yeah. So depending on a, right? So this clockwise, they are clockwise moving. If a is positive, you look at here. Here, if you look at the tangent here, what is the tangent there? What is the tangent at that point? You take no u equal to 2y, y
Yes.
equal to 1, y is positive, x square plus y square anyway positive. If a is positive, so that is along the direction, right? So that is u is positive, so that is in the direction of u, right? Isn't it?
Yes, sir. Yes, sir.
So the tangent is basically, these are your streamlines. The tangent will be uv. So just to confirm, u has to be in the direction of x, positive direction. So u has to be positive, v has to be 0. V is 0 because, why v is 0? V equal to minus ax, right? Minus ax by x square. A is positive. Why is that? X is 0, no? You're looking at x equal to 0. At that point, you're looking at it, right? Isn't it? Y is only, let us say, y equal to some constant, x equal to 0 here. If you look at here, what happens? Here x is something, y equal to 0, right? So in this case, the direction should be this way. That's what is confirmed, no? So that is negative direction, 0 comma y. Y equal to 0 and minus ax by, that is negative if a is positive. So this is clockwise if a is positive. Okay. So clockwise, that is clockwise. Anti-clockwise, if a is negative. That's the direction you can easily recognize. Okay. So that is one example. Now let's look at some other examples. For example, okay, so another, now you know this polar coordinate, right? So now you know, so you are only looking at the, now only looking at, we are looking at only the two-dimensional flow. Okay, so two-dimensional flow, we are going to look at in polar coordinates. So far you have seen that this is, you have considered xy plane, you have the flow, and your z direction is your that velocity potential. Okay, so that v bar is actually you consider as some scalar function into z direction. So how you are going to write u bar? So in polar coordinates, polar form, what is u bar? U bar equal to, now you have this. This is your curl, right? So curl. How do you write this curl? This is equal to what? You just need to look at that the formulas that I asked you to do. So what is del cross u? Del cross u you did, no? Hello?
Yes, sir.
Can you just look back? In polar coordinates means only xy. Xy del cross f is what? What is del cross f? Del cross v. What is v first of all? Okay, where v is, what is v now? 0, 0.
Psi, function of psi.
Function of psi of xyt. This is what is your v. Okay. So u is basically what you have. This u is basically uvw. Uvw 0. So this is only two-dimensional flow. So in polar coordinates, how does this look? This is equal to, yeah, what do you write?
Del by del r into del by del theta.
Dou psi by
Do r.
in polar coordinates, what is that you have? Do you have it? Do you have it in hand? Or is, let me pick up and write it. So people may, you may forget it, no?
Yes, sir.
Let me just see. We'll see and write. Okay, so these things, you at least in polar coordinates you should be familiar. Okay, for you to work out. So in polar
Okay, sir.
coordinates, del cross f will be. Shall I write directly? Will you work out?
Yes, sir. Yes, sir.
Del cross f will be in polar coordinates. I'm just writing it here. So you are expecting only r theta only, no? And 0. This is anyway, the third component anyway will be 0. So here del cross v will be, I am writing directly, just check it. So 1 by r times dou psi by dou theta. Okay, x equal to r cos theta, y equal to r sin theta. So you have this one. This is one component. Other component is, this is your r component. Okay, r cap into r cap if you want. So this is basically in Cartesian coordinates. So this becomes, this is your, so we'll write it. So when you write like this, so what is the second component? You will get minus dou psi by dou r equal to 0. So what I'm writing actually equal to u bar in polar coordinates is equal to u r first r component into r cap plus what else you have? So this is your theta component into theta direction. So that is nothing but 1 by r dou psi by dou theta into r cap plus u theta, that is given as minus dou psi by dou r into theta cap. So this is how you have to write in polar coordinates. Okay, just go and write what is your del cross v. V is with these three components in polar coordinates. You just, if you what already you have calculated now, h1, h2, h3. This is what one of you have to give the assignment.
Yes, sir. Yes, sir.
So just try to see that it is same. Unless you work out, so you will not be able to see. Otherwise, you just need to be familiar with this, at least polar coordinates immediately. So what you get is basically ur is equal to 1 by r dou psi by dou theta. U theta is minus dou psi by dou r. Okay, this is what you have. So from here you can actually calculate. Now, if you give me your ur and u theta components, then I can calculate the same way, isn't it?
Yes, sir.
So in these polar coordinates, if you write that earlier example, so what is your stream function? Psi of. So this is basically general. This is the polar form. Okay, that is done. So you basically, if you write it psi of in polar form, if you want to write your psi in this example, that is same as or equivalently. So now I can put it here. Okay, so now once you do this one, that example, so this is what is called vortex. Okay, this is a vortex flow. So whatever that example that you have given, that is called vortex. This, right? Streamlines are around this point 0, 0. So this is basically vortex flow. Vortex. So your vortex in polar coordinates you can write vortex flow in polar coordinates. So what is that one? So vortex flow in polar coordinates, stream function is for vortex flow in polar coordinates, stream function. If you want to write a stream function, psi of x, y, t, right? So that is going to be r and theta. So psi of r theta t equal to, what do you get? Log a by 2 ln of x equal to l r square, right?
R square plus theta square, sir.
Yeah, so that is actually a by 2 times ln of r square. So that is nothing but simply a ln r, right? 2r, 2 cancel, so a ln r. So a times ln r is basically your stream function in polar coordinates. Okay, so one more flow we can give, for example, source. The second example is kind of source or sink. Source or sink. So how do we give this one? So in the case, if you actually see this source or sink, it's always looking like this, right? So if it goes like this is basically sink, right? Everything going to one point, so that is sink. Source is like this, all in this direction it goes. This is source. So everything, see, if you actually see this one, flow is only in the radial direction, right? Flow is only in the R direction, R cap direction, right? So what do you expect if it is R cross that one? Yes. What is the meaning of this? Flow is only in the R direction means what? Theta cap coefficient should be 0, no? That U theta is 0, right? The theta component of the flow is 0, right? Hello?
Yes, sir.
And not only this one, UR, that R component is independent of, this is only purely function of R. Otherwise it changes, no? It's only straight lines. So that is the reason it is basically only function of R. Okay? So that's what is UR of R in the direction of R cap. This is U theta in the direction of theta cap. So it doesn't depending on theta also. Okay? So what you have is you call this simply F of R. Okay? So this implies what is your UR? UR is basically your FR. Okay, so what is this one? This we know. What is the UR component in the polar coordinates? We're trying to do
ALNR.
polar coordinates. UR is 1 by R dou psi by dou theta. 1 by R dou psi by dou theta. And then U theta, which is 0, okay, which is here is minus dou psi by dou R. So clearly, this will give me, what is your psi? Both of them you solve it. Okay, what is psi? Can you tell me what is psi?
Any constant, sir.
Huh?
I equal to function of theta.
So psi equal to psi of r theta t equal to is equal to psi of r theta equal to, it's 0, no? So it's a function of r. Dou psi by dou. So it should be function of theta, right?
Yes, sir.
Some,
Yes, sir.
let's say some g of theta. And it's constant, right? Yeah, that is your g of theta. And then this will give me, how do I calculate this one?
Differentiate, sir, with respect to theta. We have UR.
Yeah, you will get 1 by r times dou psi by dou theta equal to g dash of theta by r, right?
Yes, sir.
By r equal to, uh, yeah, that's what you can do. So this is equal to, left hand side equal to f of r. How this will now, this will give me g dash of theta equal to r into f of r, isn't it?
Yes, sir.
Now what is g of theta? So this will give me g of theta. G is only function of theta, no? So g of theta equal to r into f of r into theta, isn't it?
Yes, sir. Yes, sir.
Plus some constant. That constant anyway, if you put it, so that constant doesn't matter in your, this is your stream function, no? So g theta plus constant doesn't matter. So this is what is your g of theta. So what is this f of r? Okay, so this is r into f of r. Yeah, how do you get this f of r, function of r? We have not found this function of r, no?
So then we can take the we know psi ALNR, sir. Then we can take differentiation with respect to theta.
Which one? Which one?
We already know, sir, psi of r theta t equal to ALNR.
That is different, no? That is vertex flow. This is source flow, right?
Yes, sir. Yes, sir. Sorry, sir.
Yeah. How do you get this one? This is equal to psi theta. Yeah. So psi theta has to be um, psi theta. Okay. So that is used dou psi by dou r. Dou psi by dou r equal to 0. Is it? It's satisfying. Dou psi by dou r equal to 0. We also need to satisfy dou psi by dou r. That is u theta, right? U theta component is 0. This one. Dou psi by dou r equal to 0. Since dou psi by dou r equal to 0. So what is your psi? Psi is basically g of theta, right? Isn't it?
Yes, sir.
Dou psi by dou r equal to, so g of theta, dou g theta by dr dou r. So that is basically, if you do, what do you get here? So f r theta plus r into f dash of r theta, right? That is equal to 0. So this means theta cannot be 0. So you're trying to find fr. So fr plus r into f dash of r equal to 0, right? So this will give me, what is fr? What is fr here? So y dash, what is fr? Can you solve this simple equation? Implies f of r. So what is this one? Y dash of x, x y dash, y dash of x plus y equal to 0. How do you solve this one? Simple, right? X dy by dx equal to minus y. That implies dy by minus y equal to minus dx by x. What do you get here? Ln y equal to minus ln x plus c, right? Minus ln c, you take it, so xc. What is y? What is f of r?
Sir, y equal to minus xc from where? Then f of r equal to minus r into c.
Okay, let's do slowly. Okay, so you calculate. So here df by r into df by dr equal to minus f. Okay, so you'll get df by f, isn't it? Equal to minus dr by r. So you will get ln of f plus ln of r equal to ln of c. Is it correct? So this will give me ln of f equal to ln of c minus ln of r. So this is simply ln of c by r. So what you are getting is f of r is nothing but c by r. C is constant, isn't it? So you go and substitute there. So if you go and substitute there, your psi of r theta, okay, the psi of r theta is what? So psi of r comma theta
Theta into c, sir.
t. It doesn't depending on t, right? Source means
This is theta into c, constant.
it doesn't depend, no? So you see that both the components you don't get any t. So psi of r theta equal to g of theta. G of theta is what? F of r into f of r into
Into
theta. So r into F of r is C by r into theta. So r goes, you're basically getting C into theta. So these are your stream functions. Stream function for source or sink. Okay. So which one is your sink? Sink is sink, SINK. Okay. So how do you decide which one is source, which one is sink? Depending on A, constant A, right? How do you see the direction? UR direction, right? UR. What is UR? Now you calculate what is UR. UR component. Dou psi by 1 by R times dou psi by dou theta. Right? Dou psi by dou theta. So that is simply will give me dou psi by dou theta is C by R.
Yes, sir.
C by R. So this is the radial direction. So if C is positive, okay, this sink, okay? C is positive means what? Is going towards that. That is source. C is negative. This is sink, isn't it? Sink if basically you have to write reverse way. So source and sink if source if C is positive, sink if C is negative. Okay, based on this. U theta is anyway, what is the U theta is anyway 0, no? What is U theta? Dou psi by dou R. Dou psi by dou R minus dou psi by dou R, right? Minus dou psi by dou R. So that is anyway 0. Dou psi by dou R, so that is constant times theta, no? This if you do, that's simply 0. Okay? So this is how you see this sink or source. So you say that sink or source, okay? Sink or source flows in this basically 2 dimensions. So through stream function we have defined, we are seeing these kind of flow. Okay. Now what is the strength of this source and sink? That if you want to see, okay, so you can define something called, so you have some source, no? So whatever the source, how fast it is going from the point 0, that is the source, or how fast it is taking the fluid. So that if you want to see, basically what you do is, if you to calculate that source strength or sink strength, that is do source strength, I define it as, how do I define it as? Is basically the amount of fluid that comes out of that, right? So that is basically flux, right? Flux of the fluid from the source point. The source of strength by definition is the flux of the fluid from the origin, from the source point or sink point. Source strength or sink strength is a flux of the fluid into the source point, sink point. Okay, that's how you define. Okay, so source strength, if you can, so similarly for sink strength. So how do I define, what is this flux? Flux means what? What is the flux?
The force dot area, sir.
Flux means force into
How
area. No. Volume flux, right? So there's basically you're asking for volume flux. The amount of fluid that goes, right, goes through a surface.
Yes, sir. Yes.
So how do you get that one? How do you get that flux? Basically, it's a volume flux, right? So you're not seeing as a mass, right? So if you add that rho constant, that the density, that is basically your mass flux, right? So if you don't have rho, then it is called the volume flux. The volume flux of the fluid. Okay, amount of fluid you're asking. Okay, the volume flux, you can write it like volume flux, which we defined, right? Volume flux of the fluid from the source point. So how did we define? If you look back in the derivation of the mass equation, we have defined. So that if you call it, so that is basically the closed point, this point, no? So whatever the amount amount of fluid through this surface, this is the source point. Out of this, how much is going outside through this surface? That surface is basically in a single case circle of radius r. Okay, we call this CR. CR is the circle of radius r, and you have a velocity vector. This velocity dot product with this is a normal, right? This is a normal direction. So r direction, which is normal. This is simply a line integral, right? It's a two-dimensional flow. This is what is your source strength. So if you call this source strength, is you call this some number that you say simply source strength. You call this M. Okay. So if you do this one, so you need to calculate the left-hand side. That is what is this integral. So integral, if you put it, what is that you gain? What is your U? What is your U?
UVW, sir.
Yeah. First of all, ds, no. So if you want to do U is what? What is ds? This is the line integral. U dot n. So that is basically your scalar function. So how do you calculate? So you need to look at your those calculations that I have done for the polar coordinates. Polar coordinates. What is ds? We have written no ds at the end. If you look back those equations when we derive line integral ds also, no? ds, what is the ds? We wrote hr dr r cap plus h theta d theta cap, isn't it?
Yes, sir.
So if you remember that one, that you have to use it here. Okay. So what is that you what is that you get? Can you tell me?
Sir, actually, I forgot the formulas.
Will forget. I know, I know. So that's why I ask you to do this exercise.
Okay,
So
sir.
okay, so now we'll see. So you know what is that HR, right? So we'll calculate. So what is HR? HR in polar coordinates is simply 1. H theta is r. Okay. So HR is 1. So dr r d theta. Okay, that's all. No, that is only your only 2 dimensions, right?
Yes, sir.
So ds is basically, this is basically the ds. ds is along the tangent direction, right? That's your tangent direction. Uh, ds is a vector, right? This is the ds is a vector. So I think we have a vector or a scalar. This one, source strength. This is basically what? U ds. U dot. Yeah, how are you going to see that is? But is basically that's a vector, right? ds is vector. So if you want to integrate, how do you integrate this one? Maybe it's too much time. I think we'll see maybe next class. Okay. So how do you calculate this one? U dot n cap ds. Think over. This is
Okay,
only
sir.
line integral. S is there, but ds is basically it should be the quantity. That if you want to see as an integration, it should be like what is this line part you want? That is basically based on theta, no? It's a small quantity. R into this is r. This is r and this quantity is theta. So this quantity is basically r d theta, right? R theta, right? So if you say this is your d theta, so r into d theta should be that one. So r into d theta, let me put, okay, that is your, what is your u? So you know that n cap is basically r cap direction, right? R cap is your unit normal, right? So what is u cap? U r u theta dot product with 1 comma 0, right? Isn't it? This is what is your u bar dot n cap in the polar coordinates, isn't it? So this is your n cap is what? R cap comma 0, right? R cap 1 into R cap plus 0 into theta cap. That is your r, right? So you will have UR into 1. So that is simply UR. What is UR? What is that you got UR? UR is C by R, right?
Yes, sir.
That's your C by R. So you get C by R, you put it. So C by R, that is your C by R. So what is that now integral? So this is over, theta is between 0 to 2 pi. This is a circle, right? This is your M.
So then answer will be
So
2 pi c.
R, yes, so you will get M equal to 2 pi C. So this is your strength. Strength of your. So you in a indirect way, if you are giving some strength, source strength, or so if you say strength of some M is your strength. Okay, so then what is your stream function and the velocity, whatever. Okay, so let me write it and we'll close it. Okay, so for a source of strength, let us say M is given. M is given. Okay, source of given strength M. What is your U bar equal to? What is your UR? UR is C by R, right? UR is C by R. C is what? M by 2 pi, right? From this you can get C equal to M by 2 pi, M if M is given, into R. So M divided by 2 pi R into, this is your R cap component. And then what is the other one? U theta. U theta is 0 anyway, right? That is simply 0. This is your velocity for the source of strength M. So you basically you write like M divided by 2 pi R times R cap. That's all. This is your velocity. What is your stream function? Psi of R theta equal to, for source of strength M, equal to C by R, right? M by 2 pi into theta. C into theta is your psi, right? So what is your psi? Psi is basically C into theta. So what is C? C, you will get it right by M by 2 pi. M by 2 pi into M theta by 2 pi. This is your source of strength. For source of strength, stream function is that. This is the stream function. So this is the velocity vector, flow vector. Okay. This is the flow vector. This is your stream function. So like this you can calculate. Okay. I think rest I think we'll continue tomorrow at 11. Okay. So we'll meet at tomorrow 11, right?
Yes, sir.
Yeah, we'll see tomorrow at 11. So I hope you understand everything. So is there any questions here?
No, sir. I have
This,
to revise all those things with previous formulas.
yeah, just okay. See, now you understand now the importance of those formulas that we derived in the,
Yes, sir. Yes, sir. Yes, sir.
at least for polar coordinates, it should be in your mind. Polar and cylindrical coordinate system you should have in your mind in order to work out. Okay.
Okay, sir.
Otherwise,
Okay, sir.
difficult. You will try to recall and you will do a lot of calculation mistakes. Okay.
Yes, sir. Yes, sir.
So try
I
to be
realize that. Yes, sir.
clear and do it. Huh? Yeah. Okay. I'll see you tomorrow at 11.
Okay, sir. Thank you, sir.
Okay. Yeah. Bye.